Okay, let's just jump right into it. Today, we are taking a deep dive into an algorithm that is, well, an absolute cornerstone of computer science, quicksort.
Mm-hmm.
It's one you encounter pretty much everywhere, really fundamental to how systems organize information efficiently.
That's right. Yeah, we've been looking through some excerpts discussing quicksort, and they give us a really solid view of its mechanics, why it's so prevalent, and how it's actually been refined over time.
Right. So our mission for this deep dive is to go beyond just like knowing the name. We want to truly understand the engine under the hood,
Yeah.
how it works, why it's called quick, especially when other algorithms have the same theoretical average speed and the clever tricks developers use to make it even better, more robust. By the end, you should feel like you really get quicksort.
Okay, so the fundamental idea, what's the big picture? At its core, quicksort is a classic example of the divide and conquer strategy.
Divide and conquer. Okay,
Yeah.
explain that simply. What does that mean in practice here?
And think of it like breaking a big, overwhelming problem, sorting this whole messy array into smaller, identical problems that are easier to solve.
Okay.
You solve those smaller problems, the smaller sorts, and then somehow combining their solutions solves the original big problem.
Oh.
In Quicksort's case, the combining step is sort of automatic.
Got it. Break it down. And Quicksort applies this to sorting by using something called pivot partitioning. Is that the key?
Precisely. Yeah, this is the critical operation. The whole goal of partitioning is to pick one element, we call it the pivot, and then just rearrange the array section you're looking at,
Oh, so.
so that everything less than the pivot ends up on one side, its left side typically, and everything greater than the pivot goes to the other side, the right side.
And after this partitioning step, is the pivot itself in its final sorted spot, like locked in?
Yes, that's the key outcome. That's exactly right. A successful partition means the pivot ends up exactly where it belongs in the final fully sorted array.
Okay, that sounds pretty neat in principle. But how does this pivot partitioning actually happen? Step by step within the array. This feels like where the real action is.
It is. Let's walk through the basic process described in the material. It usually starts by just selecting the leftmost element of whatever section of the array you're currently working on. That's your initial pivot.
Okay, leftmost element is the pivot. Then what?
Then you set up two pointers, traditionally called I and J. Pointer I starts right next to the pivot, basically the beginning of the section you're sorting, and J starts way over the very right end of that section.
So pivot on the left, I starting near it, J starting at the far end. What do? Do they move?
They start searching inwards
Mm.
towards each other. Pointer J moves from the right towards the left. It's looking for the first element it bumps into that is smaller than the pivot value.
The pivot that's sitting at num's left.
Exactly, num's left.
Huh.
So J keeps stepping left, J, as long as the elements it sees are greater than or equal to the pivot. It stops when it finds something smaller or if it runs into I.
Okay, so J finds something small on the right side, and I does the opposite.
Exactly the opposite. Pointer I starts from the left, near the pivot, and moves right, I++. It's searching for the first element that is larger than the pivot, num's left. It keeps stepping right as long as elements are less than or equal to the pivot, or until it bumps into J.
So J stops on something too small for the right side, I stops on something too big for the left side. What happens if I is still to the left of J when they both stop moving?
That's the signal. It means you've found a pair of misplaced elements. Num_psi is too big for the left section. Nums_sj is too small for the right section relative to the pivot. So you just swap them. Swap the values at index I and index j.
Okay. Put them on the correct side, you swap them, and then pointers just keep going.
Right. They've done their job for those positions, so they continue the search. You repeat the loop. J searches left, I searches right, find misplaced elements, and if I is still less than j, you swap. This whole dance continues until the pointers I and j finally meet or cross each other, meaning I, ej.
Okay, they meet or cross. That's the end of the main rearrangement part. What's the very last step of this partitioning phase?
The very last step is crucial. It's placing the original pivot element, remember. It's been sitting patiently at the initial left position this whole time into its final correct sorted spot. You swap the pivot element, num's left, with the element at the position where the pointers met, which is index I. So swap num's left, num's I.
And that index I where they met, that's returned. That's the pivot's final home.
Exactly. The function returns I.
Okay, so after all that scanning and swapping within a section, you end up with the pivot in the right place. What else does that single partitioning step guarantee about the array section?
The critical property, and the source makes this really clear, is that the array section is now split into essentially three parts. You've got the left subarray, everything from the original startup to pivot 1, then the pivot itself at index I, and then the right subarray, everything from pivot +1 to the original end.
And the guarantee is?
The guarantee is any element in the left subarray is less than or equal to the pivot, which is less than or equal to any element in the right subarray. That's the key inequality.
Oh, right. So it's not perfectly sorted within those left and right chunks yet.
No, not at all. They're still jumbled internally.
But it is partitioned. The pivot is definitely sorted relative to everything else, and all the smaller stuff is on the left, all the bigger stuff is on the right. This really feels like the divide part of divide and conquer. You've broken the problem down.
Precisely. You've divided the problem of sorting the whole section into two independent, smaller problems, sorting the left piece and sorting the right piece.
So how does the full quicksort algorithm handle those two smaller pieces then? Does it just repeat the whole partitioning process on them?
That's exactly where the recursive nature comes in. The full quicksort algorithm is surprisingly simple once you have that partition step-down path. Step 1. You perform the pivot partitioning operation on the initial array, or whatever subarray you're currently focused on. This gets you that pivot in its correct spot and tells you the boundaries of the two unsorted subarrays on either side.
Right. The left piece and the right piece, like you said.
Step 2. Then you recursively call quicksort itself, but only on the left subarray. So you're applying the entire quicksort process partition, recurse, just to the elements from the original left boundary up to pivot 1.
Okay, focus on the left chunk.
Step 3. And then you do the same thing for the other side. You recursively call quicksort on the right subarray, covering the elements from pivot +1 up to the original right boundary.
So it's quicksort, calling quicksort on smaller and smaller parts. When does it actually stop dividing?
It stops when it hits what we call the base case. The recursion needs an exit condition, right?
Right.
The base case here is when the section of the array you're asked to sort has a length of 1 or even 0. If there's only one element, it's already sorted by definition. If there are 0 elements, well, there's nothing to sort. So in those cases, the recursive call just finishes immediately, does nothing, and returns.
And as these tiny calls finish, and the calls that called them finish, working back up, because each pivot was placed correctly and everything ended up on the right side of its respective pivot, the whole array just becomes sorted. It's actually quite elegant when you think about it.
It really is a very powerful structure. Now let's talk performance. Why is this algorithm called quicksort? How does it actually stack up against other ways of sorting?
Good question. Let's look at the features. First off, time complexity. This is about how the runtime scales as the input size, let's call it n, gets bigger. What does the source say?
In the average case, quicksort shines. It's O(n) log. The explanation is roughly that partitioning tends to divide the array somewhat evenly, leading to about log n levels of recursion.
Like cutting the problem in half repeatedly.
Exactly. And at each of those log n levels, the total work done across all the partitions happening at that level, all the comparisons, all the swaps, adds up to something proportional to n.
So n work per level, log n levels, gives you O(n).
Okay, average case sounds good, same as merge sort or heap sort, but I know there's a catch.
There is. Here's where it gets a bit tricky. Quicksort has a worst-case time complexity of O(n) that's quadratic, much slower.
When does that happen?
The source points out this happens if the partitioning consistently goes badly wrong. Imagine if every time you partition, you pick the absolute smallest or absolute largest element as the pivot.
So you don't divide the problem effectively at all.
Right. You end up with one subarray that's empty or has one element, and the other subarray has almost all the elements.
Yeah.
If this happens repeatedly, the recursion doesn't get shallow, like log n. It gets deep, potentially n levels deep.
And you're still doing about n work scanning at each level?
Exactly. N levels times n work per level. That's yikes. Sounds pretty bad compared to, is that like a common problem you hit in practice?
It can be, especially with certain kinds of input data if you use the naive pivot selection. For instance, the basic implementation that always picks the first element. It performs terribly on already sorted or reverse sorted arrays. They trigger that worst case every single time.
Okay.
It's also noted as non-adaptive sorting. That means even if the input array is already mostly sorted, quicksort doesn't really speed up significantly. It still has to go through the motions.
Gotcha. Okay, what about memory usage? How much extra space does it need?
For space complexity, quicksort is generally considered in-place sorting. This is a big plus. It mainly modifies the original array directly. It doesn't usually need a large, separate temporary array like merge sort does,
There's always a but.
but it does use space on the call stack for those recursive calls. And guess what? In that same worst-case scenario for time where the recursion gets really deep levels,
Let me guess, the stack space also blows up.
you got it. The stack space used can also reach in the worst case. So the worst case for time often means a worst case for space too, at least for stack usage.
Okay, so the worst case hits you on both time and space if you're unlucky or using a basic version. And one more feature, stability. Does it keep elements with equal values in their original order?
No, the source clearly states it is non-stable sorting, and it gives a specific reason, that final swap in the partitioning step.
The one that puts the pivot in place.
Yeah, when you swap the pivot, nums left, with numsci, the pivot might jump over elements that were originally to its left but happen to be equal to it.
Hmm.
This changes their original relative order. So if you have duplicate numbers, quicksort doesn't promise they'll end up in the same relative order they started in.
Okay, summing up, average time nice, but potential worst time and worst space, plus it's not stable. Honestly, that list of features doesn't immediately scream quickest algorithm ever.
Right. It
Yeah.
seems a bit mixed.
So why is it often called quick? And why is it so incredibly widely used in libraries and systems? What makes it fast in practice?
That really is the million-dollar question. And the name isn't just hype. It generally is faster in the real world for typical inputs compared to other algorithms with the same average, like merge sort or heap sort. The source points to a few key reasons that go beyond just the big O notation.
Okay, lay 'em on us. Why is it quick?
Reason number one, low probability of worst-case scenarios for typical data. While that nasty worst case exists, it usually requires specific, often structured inputs, like those already sorted arrays we mentioned, especially for the basic pivot choice.
Mm-hmm.
With randomly ordered data, or the kind of messy data you often see in real-world applications, it's just statistically much more likely that the partitions will be reasonably balanced. The performance stays much closer to the average. So the bad case is less likely to bite you in everyday use.
Okay, so the theoretical worst case, while real, isn't hit that often in practice. What else makes it fast?
Reason two, high cache utilization. This is a really important factor, kind of a hardware interaction thing that big O notation completely ignores.
Cache utilization, like the CPU cache.
Exactly. During that partitioning process, the algorithm is mostly just scanning and swapping elements within a relatively confined section of the array. Those elements are usually located close together in the computer's memory.
Right.
The CPU can load these nearby elements into its superfast cache memory very efficiently. Accessing data from the cache is way faster than fetching it from main memory. Algorithms that tend to jump around more in memory, like heap sort while building its heap structure, don't benefit as much from this locality of reference.
Ah, okay, so it's not just about the number of operations, but how fast the computer can actually perform each operation, because the data it needs is often right there, readily available in the cache. It's like sorting papers all laid out neatly on your desk versus having to run around the room to find each paper.
That's a perfect analogy. And it leads to reason three, small constant coefficient. This is another subtlety hidden by big O. Even if two algorithms are both, say, log, one might perform slightly fewer actual basic operations, fewer comparisons, fewer swaps, fewer assignments for the same input size.
Mhm.
The source notes that quicksort, when implemented well, generally has a smaller constant factor. It does less auxiliary work per element compared to merge sort, which involves copying to temporary arrays, or heap sort, which involves heap maintenance.
So sticking with the car analogy, maybe two cars have the same theoretical top speed, but quicksort is like the more aerodynamic car. It has less algorithmic drag, so it reaches that speed faster and performs better overall.
That's a great way to put it. Fewer operations overall, combined with that fast data access via the cache, makes it really zippy in practice most of the time. The source compares it to why insertion sort, though worst case, is often faster than bubble sort for small lists. Insertion sort just does less junk work per step. Quicksort has a similar kind of low-level efficiency advantage on a larger scale.
Okay, that makes a lot more sense now. It's fast because of good average behavior, excellent cache friendliness, and fewer actual operations per step. But we still know that worst case and the potential space complexity from deep recursion are real weaknesses. Can developers do anything about those? Can quicksort be, like, made safer?
Absolutely. And they have. Algorithms aren't static things, they get refined. Quicksort has some really well-known classic optimizations specifically designed to tackle its biggest weaknesses. The source material highlights two particularly important ones: pivot optimization and tail recursion optimization.
Okay, let's break those down. Start with pivot optimization. The problem is that a bad pivot choice leads to unbalanced partitions and that awful time,
Yeah,
so the fix must be about picking a better pivot, right?
exactly. The naive approach of just grabbing the first element is simple to code, but it's just too vulnerable. Sorted arrays, reverse sorted arrays, arrays with lots of duplicates near the start, they all lead straight to the worst-case partition, where the pivot is the min or max, leaving one side empty and the other huge.
You mentioned picking a random pivot earlier as one idea.
Yeah, random selection is a common technique. It helps tremendously because it makes it extremely unlikely that any specific malicious input will consistently trigger the worst case. It sort of spreads out the risk.
And not foolproof.
Well, the source notes that since computers use pseudo-random number generators, it's theoretically possible, though maybe unlikely, to craft an input that still exploits the predictable pattern in the pseudo-random sequence. It's much better, but maybe not perfect protection against a determined adversary.
Okay. Is there a more common deterministic way to get a good pivot?
Yes, and the source focuses on what's probably the most popular technique, the median of three optimization.
Median of three. What's the idea?
It's pretty straightforward. Instead of just blindly picking one element, like the first one, you look at three candidate elements within the subarray you're about to partition. Typically, you pick the very first element, the very last element, and the element right in the middle of that section.
Okay, first, middle, last. Then what?
You find the median value among just those three. Not the average, the median, the one that would be in the middle if you sorted just those three values.
Got it. The middle value of the three samples.
Exactly. You
Yeah.
take that median value and you swap it into the very first position of the subarray index left.
Hmm.
Why there? Because that's where the standard partitioning logic we discussed earlier expects the pivot to be.
Ah, okay. So you prep the partition by putting a better pivot candidate in the standard starting spot.
Precisely. And then you just proceed with the normal two-pointer INJ partitioning process,
Yeah.
using this median of three value as your pivot.
How does choosing the median of three help so much in avoiding the worst case?
By sampling three positions, you dramatically increase the probability that the pivot you choose is actually somewhere near the true median of the whole subarray. It's much less likely to be the absolute smallest or absolute largest element.
It pushes the pivot towards the center.
Exactly. It gives you a much better chance of getting reasonably balanced partitions, which keeps the recursion depth closer to log n and steers you away from that cliff. The source even mentions you could extend this median of 5, median of 9, for even more robustness, though with slightly more overhead in picking the pivot. Median of 3 is usually the sweet spot.
Okay, that makes sense. Median of three is a great fix for the worst case time complexity by improving pivot quality. What about the other potential problem? The worst case space complexity, that stack depth issue from deep recursion.
Right, that's tackled by the second optimization, tail recursion optimization. The problem, again, is when the recursion gets very deep because of those unbalanced partitions, potentially using up way too much memory on the program's call stack.
So if one side of the partition is always tiny and the other side is huge, the recursive calls just keep stacking up deeper and deeper.
Precisely. This optimization cleverly avoids that. Here's how it works. After you perform a partition, you have your pivot in place, and you know the sizes of the left subarray from left to pivot 1 and the right subarray from pivot plus 1 to right. You simply compare the lengths of these two resulting subarrays.
Compare their sizes.
Okay.
Okay, and then
And then you only make a recursive call for the shorter of the two subarrays.
only the shorter one. What happens to the longer one? Does it just get ignored?
No, not ignored. Instead of making a second recursive call for the longer subarray, you handle it iteratively. You simply update the boundary pointers, left or right, of the current function or loop to narrow the focus onto that longer subarray. Then the main loop of the quicksort function just continues, and on the next pass, it will naturally process that longer subarray.
Ah. So you only actually go deeper in the stack for the smaller half. The bigger half is handled by just adjusting the bounds and letting the current level loop again. That's clever. It avoids making two recursive calls per step.
Exactly. It effectively turns one of the recursive calls into an iteration, specifically the one for the larger subproblem. This is a form of tail recursion optimization, because you always recurse on the shorter side, and the shorter side can be, at most, half the size of the current problem.
The maximum depth of the actual recursive calls can't be more than a log.
You nailed it.
Yeah.
This optimization guarantees that the maximum recursion depth is limited to even in the worst-case partitioning scenarios.
That's brilliant. So you transform a potentially stacked depth problem into a guaranteed stack depth, which is way, way better and much safer for memory.
Yes, it makes the algorithm far more robust in terms of space usage, especially crucial for very large inputs or systems with limited stack space. It addresses that worst-case space complexity directly.
Wow. Okay, we've really covered a lot of ground here. We went from the basic divide and conquer idea through the nitty-gritty of the partitioning process with I and J, the recursive structure.
Looked at the performance characteristics,
Yeah.
the average versus the O-case, the in-place nature but potential stack issues, the non-stability.
Right, and then why it's often faster in practice, cache locality being a huge one,
Hmm.
smaller constant factors, and finally, these really important optimizations like median of 3 for time and tail recursion for space.
We've definitely taken the source material and tried to build a really solid layered understanding of quicksort. Hopefully you feel like you've seen it from multiple angles now.
Absolutely. So, after digging into all of this, what does understanding quicksort really mean for you listening right now? Why should you care about these technical details?
Well, first off, I think it's just a fantastic, concrete illustration of divide and conquer. That's such a fundamental problem-solving pattern, not just in coding, but, in breaking down any complex task. Learning quicksort gives you a really clear mental model for how that works.
Yeah, I agree. It also gives you, I think, a masterclass in the nuances of algorithm performance. It really hammers home why just looking at the average big O notation isn't the full picture.
Definitely.
The worst case does matter, and these subtle factors like how an algorithm interacts with hardware, like the cache or the exact number of operations hidden in the constant factor, can make a huge difference in real-world speed.
And maybe most importantly, it shows that algorithms aren't just these static, perfect things handed down from above. They can be, and often are, optimized. Seeing how clever thinking like picking a better pivot or restructuring the recursion can directly address an algorithm's weaknesses is a powerful lesson in itself. It's about iterative improvement and smart problem solving.
Totally. And I think ultimately diving into something like Quicksort helps you appreciate the really sophisticated and efficient ways computers manage the insane amounts of data we deal with every single day. Sorting seems basic, but doing it fast is critical, and Quicksort is a prime example of high-performance computational thinking.
It really gives you an insight into efficiency that kind of sticks with you, I find.
So we've sliced and diced Quicksort. We uncovered its core divide and conquer heart, walked through the intricate dance of pivot partitioning, dissected its typical speed against that lurking threat, and revealed the clever optimizations like median of 3 pivots and tail recursion that tame its risks and conserve memory.
Yeah, we saw how identifying the weak point, the pivot choice, could drastically improve time, and how restructuring the process, the recursion, could save significant space.
Thinking about that, we optimized Quicksort by pinpointing the element causing imbalance, the pivot, and the process consuming too many resources, the deep recursion. How might that core idea identifying the critical element or the bottleneck in a system, and then specifically restructuring the process around it, apply to problems you encounter in completely different areas, maybe far beyond just sorting numbers, something to think about.